All right, let's look at an example of unsteady flow, shall we? I'm going to go ahead and switch to the document camera. You don't need to see me anymore. You guys, some of you have been following along. You know how this goes. I'm going to write this out on paper, all my givens. You can see the problem statement there, and and then I'll zoom in here. Okay. So my given information here, I've got R134A, that's refrigerant 134A. That's a fluorochlorocarbon. I forget which one it is. Um, anyway, we've got a rigid tank, 2 gallons. And there's an initial pressure, 120 psi, pounds per square inch absolute. An initial temperature, 90.5 degrees Fahrenheit. We're going to open a valve on this tank. Maybe I always walk through kind of a scenario that we've got a repair person come into the house, get a refill our air conditioner system, and they've got this 2 gallon tank of R134, big old tank they carry in, and they just managed to drop it on the way in. That release the valve opens up and releases some material out. And I don't know if these numbers are realistic at all. It seems like a pretty big pressure drop. So the tank's going to be open for 3 seconds, and in that 3 second span, we've got a pressure gauge on the tank, and it tells us it's now 60 psia. It was a hot day outside. 90.5 is sitting in the van, so it's just kind of become close with the ambient temperature, 90.5. And then after the valve's been cracked open, the remaining material inside expands, goes to a lower energy state. And so the remaining material inside goes down to all the way down to 60 degrees Fahrenheit. Somehow we've got some way of measuring the temperature inside the tank. Pressure is easy. You got some pressure valve on it. Temperature is a little harder, but we've got thermal, infrared ray guns. You basically can shoot at these things now and get a temperature reading. Again, this occurs over a 3 second period. So those appear to be our givens. What are we looking for? We're looking for find m dot. Find m dot. Got an example problem. Okay, I'm going to stop share and go to the document cam here. Okay. All right. Well, here I would ask my class, all right, what's a good tool we might use here? And somebody might say the mass flow rate, and that might get us by. I did have somebody last semester say, well, can't we just do it with conservation of mass? Actually, yeah, it's pretty straightforward if you do it with conservation of mass, but let's do it just for funsies. Let's use the first law, shall we? It's a lot more involved, but it's good practice. So what do we got? We got a tank with a valve, and that valve opens. That valve's got some sort of some sort of turny thing to open the valve up, and that valve is attached to a tank, and that tank is, we're going to be open and spewing out carbon tetrafluoride or something like that. It's not carbon tetrafluoride. But anyway, if we do a first law analysis, I say, all right, what's crossing the boundary? Mass. That's it. I think we're going to assume that there's essentially no heat transfer. Why? Well, we don't really have any tools to find it. They didn't ask for it. And basically, if we heated this thing up at all as it was, excuse me, as it was losing mass over 3 seconds, then maybe our mass flow rate would go up. But we don't have that information. And this is one of those times where if they say the process occurs rapidly, this is one of those few times where, okay, this would actually make sense. I don't normally like using that. The process occurs rapidly. There are a lot of thermodynamics texts that will say that if they want you to neglect heat transfer, they'll say process occurs rapidly. This particular textbook we use does not. But this is a situation where that assumption would make sense. So we're going to assume that there's no heat transfer. I don't see anything doing work. There's no electricity going into it. There's not a paddle wheel or something in there stirring it up. We're not applying any additional force to it. So the only thing, when I write my first law equation, that is, sorry, minus E dot mass out is going to equal, and assume, again, we're going to assume uniform flow. So we're going to say change in the energy of the system, delta E system over delta T, because we're going to make the uniform flow assumption. Okay, well, fair enough. Now what? Well, let's look at the terms here. I've got delta T, that's known. The mass, the energy of the mass out. Let's expand that. So minus, it's going to have an m dot to it, and it's going to have an h out. And this m dot, by the way, is what we're looking for. So this is the energy of the mass out. Now, notice that I did not include speed. Who can tell me why I didn't include speed? And somebody will say, Steve's checklist. Yep, Steve's checklist. Do you have the speeds? No, I got volume, but that's not speed. That's a different V. So it's not given. It didn't ask for the speed directly. They're just asking for the mass flow rate. That's not actually the speed. It's not technically a nozzle or diffuser. There's kind of a nozzle right there. If I knew the area of that outlet right there, then I might be able to figure out the speed. I might be able to, put the mass flow rate in terms of speed. I'd end up with a third order polynomial we'd have to solve, and probably a solver. Not impossible, but for simplicity's sake, let's assume it's not a nozzle or diffuser. And let's assume that since I was not given the area, I probably can't find the speed very easily. So if in the case that we're going to say no to all four of those, we said last time, we're just going to assume that the enthalpy term is much larger than the kinetic term. So we're going to assume it's not that there's no speed at the outlet. That's not what we're assuming. We're just assuming that the speed is not going to contribute significantly to the energy of the mass out compared to the enthalpy, for example. Okay. All right. So if that's the case, well, this is the energy of the mass out. And we're going to set that equal to the change in the energy of the system. Well, it's essentially stationary. So here's where I would ask the class, okay, what are the types of energy that can change for my system? What does this comprise? And I'll wait until I get an answer. So if you know, go ahead and write that down. If you don't know, go look. What should be included in delta E system? I'm pausing here to give you a chance to go look, and pause if you need to pause more. All right. Hopefully it came back and said, well, it's closed, or I'm sorry, it's not closed, but it's stationary. So since it's stationary, the only type of energy that's going to change is the U value, delta big U, divided by delta T. Okay, so these are, again, the energy of the system is going to be the internal kinetic and potential energy of the tank itself, not the mass. That's here, right? The mass has energy here, but the tank itself, the system itself, it has internal kinetic and potential energy. And the only one that's changing there significantly is going to be the internal energy. Okay. All right. So I'm going to move delta T over here to this side. So that's going to be minus m dot H out times delta T. And that's going to equal, it's going to be M2 U2 minus M1 U1. And here I would pause and I would ask the class, okay, why do I have two different masses here? And so think about that, have an answer. Why do I have two different masses there? Well, the answer here is, well, what exactly are we trying to do with this problem? Remember, the whole purpose of the problem is this tank's losing mass. The valve has been cracked open. We want to figure out how fast is it losing mass. So therefore, the mass is going to be different from the initial to the final state. So you're going to have two different masses there. Okay, cool. Um, so let's look at our properties here, right? I'm looking for m dot. H out is a property. Delta T is given. I don't know the masses. What about the U values? Well, the properties H and U are all going to be properties. That means I got to follow the rules for whatever the substance is. It's the first question when I'm trying to find unknown properties is what is my substance? Well, my substance is R134. So I got to follow rules that we've talked about for finding properties of R134. What do I need to know to find properties of R134? I need to know two properties at each state. I've got initial state. I know pressure and temperature. That should be enough to find U1. I guess this is U1. Sorry. U1. I apologize. So I know enough information, should know enough information to find U1, given pressure and temperature. Given pressure and temperature at state 2, I should be able to find U2. Now, what about H out? Ooh, is that state 1? Is that state 2? What do we do with that? And what we often find is H out is going to be, it's going to be somewhere between H1 and H2 from a practical standpoint. Okay. It's going to be somewhere between state 1 and state 2. We don't know exactly where. What we can do, we can use the average, if you like, as H out. Or if we stick strictly to uniform flow, we could say that H1, that basically H out, uniform flow says that the properties coming out of the system are constant, meaning it should start at state 1 and stay reasonably constant at state 1. I would not mark either of these wrong. Again, I'm not going to put this problem on a test. I'm not even going to ask my students to do a homework problem. I'm just saying I would use one or the other. If I was actually doing an analysis to try to, write up a report for, I don't know, the EPA, how much mass is actually being lost by this tank as a result of this incident? Do we need to call out a hazmat team? Well, I would probably establish a range. I would probably calculate it for H2. I'd probably calculate it for H1 and say the answer is somewhere in between. Okay. So we're estimating here. There's not really a wrong answer. Well, there are plenty of wrong answers. As long as you're using an H somewhere between H1 and H2, you can't really argue too much with it. Okay. So we can find U1, U2. We can find an approximation for H out. What about the masses? Do I know the masses? I don't know the masses. How do we find the masses? I'm pausing here. Hopefully you coming up with an answer. So if you don't know it yet, pause, come up with an answer. How do I find these masses based on what I know? How do I find the mass at state 1 and the mass at state 2? Well, remember, you know the total volume. Since I know the total volume, I can then I can say M1 is going to equal the total volume, which is constant, divided by the specific volume at state 1. Because M times the little volume is, or basically specific volume is total volume divided by mass. So if I solve this for mass, then I can find the mass from the total volume, which is known, divided by the specific volume, which if I can find U1 and U2, that means I can also find specific volume at 1 and 2. Okay, so clear path to a solution, right? Now, if we were in class, we'd go ahead and solve this out. It's already in, and what I would suggest to you is if you want to pause at this point and go ahead and find these properties, that is a wonderful exercise. You really should do, and you should be, as you're starting to see, that is a step in the problem solving process that you need to start getting really, really good at. If you're struggling to find, if you're like, hey, Steve, I don't know how I'm going to find U1, U2, V1, V2, you are really behind at this point because this is not going to be a test problem, but if it were a test problem, right? If this were a test problem out of 25 points, this would be worth at least 10. Finding the mass, understanding how to find the masses would be the remaining 5 out of 15 to get you to a D. I would give you then 5 points to find the properties. The U's and the V's would be another 5 points to find the properties. Right. So you're at 20 points at that point. That's a B. And now you just actually getting numbers to get to an A is what it would take. This is L13, page 2. This is going to be page 2 of 2. Put 2 up here so I keep track of these. So again, at this point, what you would need to do is go find your properties. Given P1 and T1, I should be able to find U1, V1, and let's go ahead and find H1 because we don't know whether we're going to use H1 or H2. So let's go look at that. I'm going to share screen here. Actually, yeah, I'm going to share screen and I'm going to pause real quick and go look these up so this video doesn't get too long. All right. So we said our pressure is 120 PSI, right? So this is R134 English units, values, round values of pressure. So we go down here and notice that at 120 PSI, these are my properties. If it's saturated, are we saturated? Well, notice that at this pressure, the temperature is 90.49. 90.49. Now, I could interpolate, I could go to the superheated table and interpolate between 90.49 in the next row to 90.5 because that's what was given to us. T1 is 90.5. I would suggest you in this case, this is one of those cases where we would say, you know what, that is right at and just slightly above saturated vapor. So I would not, you would not change the fourth or fifth significant figure on these values if you just used the value for saturated vapor at the given temperature, right? This would be very close to the saturated vapor value. So that's what we would use. We'd use saturated vapor value here for V. This guy, we'd use saturated vapor for U, this guy, and we use saturated vapor over here for the H, that guy. Okay. All right, let's go find the other state. The other state is 60 degrees, I'm sorry, 60 PSI and 60 degrees Fahrenheit. So notice at 60 PSI, this is my superheated vapor blocks. At 60 PSI, I've got a boiling temperature of basically 50 degrees Fahrenheit, and we're up at 60. So that puts us over here in the superheated vapor table. So these are my VU and H values for R134 at 60 PSI, 60 degrees Fahrenheit. This would be state 2 values. Okay, so we would record those. So you see here, we've now got given P2 and T2. I would also need V2, U2, and we'd go ahead and record H2 in case we decided to use it. Okay. Now I'm going to stop share. We'll go back to our screen here. And actually, I'm going to go back and share because now I'm just going to go, we're just going to go look at the solution. So once you've got these properties, then again, I'm down to right, one equation, one unknown, because now I know these specific volumes. I know the total volume. I've got my H's, or at least I can make a decision as to what I call H out. I would probably just call it H1. So now everything's known. Right, it's now one equation, one unknown. Now let's just go solve. All right. So I'm going to share screen and let's go look at the solution. No sense in me working it out. Again, if you want to pause at this point and work it out and then come look at the solution, do that. Okay. All right, let's go look at the solution. By the way, you want to convert those gallons into cubic feet so we can actually use those with our normal unit set. That's just a conversion we'd go look up on the internet. So here's the derivation as we worked it out. We need to know mass as volume per specific volume. So far, so good. All right, so that's the same equation we have, right? This guy right here is what I've got up here. So far, so good. Oh, and there's our properties, by the way. So far, so good. Okay. Now I just plug in, and you're going to get m dot down here of about 0.11 pound mass per second. Normally, and that's using H1 for H out. A lot of times I'll tell students, hey, okay, let's try it with H2 as H out. And I think I didn't write it here, but I think H2 is like 112 BTUs per pound mass or so. So not a huge difference compared to H1. So if you recalculated it based off of H1 of 112 or so, or 113, whatever it is, you'd find this is only like 0.113 pound mass per second. So it's not a huge difference. We're only doing this for 3 seconds, right? This is only going off for 3 seconds. So we're talking about a third of a pound in any case. It's not a huge amount of material. You wouldn't want to breathe that in. That's going to get you sick, if not kill you. But as long as you're not, as long as you're in, this is outside, then it's probably not too big a deal. Okay. It's not ammonia, right? If you ever drive by an industrial refrigeration plant, industrial food plant, freezer plant, something like that, or meat processing plant, and you see the workers get out of the building and they run. You look up on top of the building, you see which direction the wind is blowing, and you go upwind as quickly as you can because if ammonia is leaking, that is toxic. We don't put that in residential environments. But refrigerants like R134, it's not quite as toxic. You wouldn't want to breathe this in, about a third of a pound of it, but probably not fatal. I don't know. At any rate, hopefully that helps. The reason I like talking about this, right? Why do I like talking about this problem? If I'm not ever going to test you on it, it's this idea right here. Notice that this is the energy of the mass out. This is the energy inside the system. Why am I using U's and H's together? And why am I using U's in one place and H's in the other? A former student of mine one time said, so you're telling me you know flow. You know flow, yes. If for the mass that's not flowing, the stuff that's inside the system, we're going to use U values. You know flow. But for the mass that's flowing, remember it doesn't flow spontaneously. It flows because something's pushing it. What's pushing it? The mass inside trying to get out, pushing it out of the way with pressure. That pressure gets applied through volume. U plus PV gives us H. So for the mass that's flowing, the mass that's coming out, I've got to use an H value because it's flowing. The mass inside the system, we're using U values because it's not flowing, it's just sitting in the tank. So it just has a U value because you know flow. Hopefully that helps. I know it's kind of silly, but I mean, that's stuck with me for probably 10 years at this point. Hopefully it helps you a little bit. I like doing this problem because it forces us to really wrestle with when should I be using U's, when should I be using H's? If I'm talking about mass inside a system, I should only be using U's unless I've got that one very specific scenario. Yeah, I got it. I have it laying around here. This is the only time I would use H's for a closed system constant pressure boundary work, right? So go back to a few videos back, like lecture 8, 9, where we derive that, make sure you understand that. Otherwise, I should not be using H's for stuff inside the system. I should only be using H's for stuff that's flowing because you know flow. All right. This video is a little longer than I wanted it to be, but I wanted to go ahead and get it finished. It didn't make sense to break it up into 2 videos. Let me know what you guys need help with, what you think. Feel free to comment down there or send me an email. All right, guys. Next time.